Section 20.5, alternating current. So in one of the earlier videos, we mentioned the difference between alternating current and direct current, where direct current is such that the current always flows in one direction in the circuit, and alternating, it alternates directions. And this is what happens with anything you plug into the wall. So electricity that we have in households comes from an AC generator at a power station. We'll get more into why generators create AC power. But that travels through wires to get to your house. So if you plug in something like your toaster oven will get the AC source of current. So the current will flow one way through the resistor, which is a heating element. The heating element is usually a thin wire of some resistance R, and then it'll flow the other way, and it'll keep going back and forth, and that heating element will get quite hot. So in an AC circuit, the charge flow reverses direction periodically. So this isn't some random thing. It turns out it follows a nice sinusoidal path, where for some amount of time, one side of the generator is positive and the other side is negative, right? We could draw that in here in our circuit diagram, that we have a plus and a minus, and it approaches a peak voltage, V0, which we can note here is the peak voltage. And then it decreases from that peak voltage down to 0 very briefly, and it actually then goes the opposite direction. So all of a sudden, the side that had been positive now becomes negative, and the side that was negative now becomes positive. And so this is known as a negative peak voltage because it's going in the opposite direction. It increases up to that peak, down, and then decreases in magnitude back to 0, and the cycle begins again. So you can describe the voltage at any given instant, right? If this is a plot of voltage versus time, you can describe the voltage as the peak voltage times sine of 2 pi times the frequency times the time of interest. So the frequency here is set by the generator or the source of AC. And then the time will just depend on, like I said, your time of interest. And we're here going to focus on circuits that just have an AC generator and a resistor, and that simplifies things. We'll see more complicated ones in later chapters. So in circuits that contain only resistance, the current reverses direction each time the polarity of the generator reverses. So we can calculate our current with Ohm's law. Current is equal to V divided by R. But the voltage is changing with time. So if we plug in our voltage equation, it's now the peak voltage times sine of 2 pi frequency times time. And we can note that the numbers in front that are not sine, they're not time dependent, is the peak voltage divided by the resistance. This we can then call the peak current, where the peak current is equal to the peak voltage divided by R. And R doesn't have a subscript because R is the same regardless of the polarity. It's just the resistance. So now we've figured out how current varies with time and how voltage varies with time. It turns out they both follow the sinusoidal shape. And what we're often interested in electric circuits, especially with alternating current, is what the power is. So remember, power is current times voltage. So we're going to use both of these equations together. So if power is current times voltage, we'll bring in our current as a function of time equation and our voltage as a function of time equation. So we'll have our peak current times our peak voltage in front, and the sign is the same for both of these, sine of 2 pi ft. So it becomes sine squared of 2 pi frequency times time. And if you're plotting a sine squared, then it no longer goes around 0. It goes from 0 up to the maximum value and back down to 0. It always stays positive if it is squared. You could also then look into, okay, we know that the peak power is given by the peak current times the peak voltage. That's the very largest amount of power that you can have. But how much power do we have on average? What's our average power? And you can note the average power by drawing a bar over it. And if we take the average of sine squared as a function of time, the average of sine squared comes out to 1/2. That's a math idea. So then we just have the peak current times the peak voltage times 1/2, and that will give us our average power. So it's right in between 0 and the peak amount of power is our average power. That's actually really convenient. Let's dig in a little more with that idea. So if we write it instead as average power is peak current times peak voltage divided by 2, so I'm just putting the 2 in the denominator here, multiplying that out, then that suggests a different way we could split the 2 up. What if we wanted to write the 2 underneath the I0 and the V0? Well, then we could write it as a square root of 2, right? Square root of 2 times square root of 2 will just get us back to 2. But now we have I0 divided by square root of 2 times V0 divided by square root of 2. And this introduces another new variable that's helpful when talking about alternating current circuits, and that's the RMS, or the root mean square current, and the RMS voltage. So the I0 here is the RMS current, and the V0 divided by the square root of 2 is equal to the RMS voltage. So these are useful equations to allow you to go back and forth between the peak voltage and the RMS voltage. Both are reported depending on the context, so that's why it's useful to know both. All right, so now that we know the average power is the RMS voltage times the RMS current, we note that we could also use Ohm's law here to rewrite our average power in terms of just current and resistance or just voltage and resistance. Now notice in Ohm's law, as before with the peak ones, the RMS voltage is equal to the RMS current times R, where the resistance doesn't have an RMS subscript because it's constant. It doesn't matter what part of the cycle it's in, the R will stay the same. So if we follow the same procedure as we did before with our power equation, just adding an RMS subscript to the current or voltage, we find that we could also calculate the average power with IRMS squared times R, or with VRMS squared divided by R. Let's try this out with an example. So electrical power sent to a loudspeaker. A stereo receiver applies a peak voltage of 34 volts to a speaker. The speaker behaves approximately as if it had a resistance of 8 ohms. Speakers are roughly resistors. It's not perfect, but it's a reasonable approximation. Determine A, the RMS voltage, B, the RMS current, and C, the average power for this circuit. All right, so let's check what we've been given here. We have this 34 volts, so we know that that is a voltage, but what kind of voltage is it? That's part of the challenge with these problems. Notice it tells us it's a peak voltage. Okay, cool, so we know that is our V0. And one of the things we want to find is the RMS voltage. So VRMS. What else do we have here? Well, we also have the resistance is 8.0 ohms. So we can write that in here. And we're solving for the RMS current. Now with this RMS current, notice they didn't tell us the peak current, so we can't follow the same procedure as we did in A of using the peak voltage to get to the RMS voltage. So we'll need to think more on that. And then in C, it's asking for the average power for the circuit. So I'll just note that as P average is equal to what? So let's go through each of the parts and brainstorm here. So for the RMS voltage, we know the peak voltage, and that's really helpful because remember the RMS voltage is just the peak voltage divided by the square root of 2. Now, as mentioned, we can't follow the same procedure to find the RMS current, but we do know the resistance. How can the resistance help us? Well, if we know the RMS voltage and the resistance, then we can use Ohm's law to figure out the RMS current. So IRMS is just going to be equal to VIRMS divided by the resistance. And then finally, we want the average power for the circuit. And we know we can get the average power if we just have the RMS current and the RMS voltage. And we can multiply those together Bada bing, bada boom. So let's check it out. All right, so our RMS voltage is the peak voltage 34 divided by the square root of 2, so it comes out to 24 volts. RMS current, we can then take that 24 volts and divide by the resistance, 8 ohms, and we come out with 3.0 amps. And then the average power is just the RMS current times the RMS voltage, which we already solved for. So we can multiply those two together and we get 72 watts. And so that tells you how much power this speaker is using, which doesn't seem like that big of a speaker, but that's a pretty good amount of power. So maybe it's a bigger speaker than we thought. All right, one more application of power. Let's look at a conceptual example, extension cords and a potential fire hazard. During the winter, many people use portable electric space heaters to keep warm. Sometimes, however, the heater must be located far from a 120-volt wall receptacle, so an extension cord must be used. However, manufacturers often warn against using an extension cord. If one must be used, should a long extension cord used with a space heater be made from A, larger gauge wire, example 20 gauge, or B, smaller gauge wire, example 14 gauge. Why? So I want you to think about this, see if you can come up with an explanation before you move on in the video. So go ahead and pause the video now. Right, I trust you did that. So with space heaters, the basic way that they work is that there's a thin piece of wire that you run current through and it becomes hot. And that then heats up the room. And the amount of power, amount of heat that goes into the room can be given by the equation, the RMS current squared times R, right? However much resistance we have in that wire in your space heater times the current squared passing through it. Now, if we add an extension cord, the extension cord is going to add more resistance to the wire because it's making the wire longer. This is significant when you have large amounts of current passing through it, which these space heaters draw. So if we have large amounts of current passing through it, then we can start to actually heat the cord itself. Instead of heating just the space heater, the resistance in the cord might start to heat up, and that can then cause a fire, which is a bummer. So what we want is we want to minimize the power that is lost through the cord. We don't want to heat up the extension cord. What does that mean? It means that we want to keep our resistance low so we don't lose too much power into just heating the cable. In order to have a lower resistance, we want to have a thicker wire. Now a thicker wire, like 14 gauge, is actually a smaller gauge wire. Smaller gauge wires have a thicker cross section to them. And that's why when you use an extension cord for something like a heater, you really want to make sure you have a thick wire and not one of the, the super thin ones, because those could start a fire. It's a definite problem. So with your space heaters, wherever you have them, I know I have one right near me, make sure if it's not plugged into the wall that you have a good extension cord, because we don't want to start any fires, even though you would now know the physics of why there would be a fire. All right, send that power into heating you up, not heating the cord.